Okay, yeah, it's all right. Okay, that's a good start. All right, can we see it? Okay, I will just take a seat too. Yeah. All right. Hello, everyone. My name is Dhruv, and I'm a research scientist at DeepMind, and I'll be starting as an assistant professor at Princeton this year. So for today's talk, I think this is a very exciting workshop because we're kind of presenting a lot of different aspects of robotics in the CVPR community. So I want to focus on this notion of generalist robots, general purpose robotic policies, which if you've been on Twitter recently or the news or honestly any source you get your updates on research from, this word is very popular. Everyone, tells what this means. So maybe scoping it down a little bit in terms of a generalist manipulation policy, I want to throw this back to the audience. When you hear the word generalist robot, what does this mean to you? What does a generalist robot policy mean to you? It controls different robots, works in different ways. How do you interpret it? Can you just put your hands up? Go ahead. Multi-embodiment. Multi-purpose, yeah. Multitask, yes.
Multi-terrain, maybe.
Multi-terrain, yeah. So, all of them. I try to kind of expand this word cloud as people suggest more things, but more or less, to different people, this word means a lot of different things, and it's really hard for me to accept or deny any of these definitions because there is no definition. We just kind of made this up, and we call it whatever we like. So for today's talk, what I'm going to do is I'm going to give you an example and maybe a somewhat concrete definition of what one possible version of a generalist policy could mean, and then how we would, how we build it, how we evaluate it, and so on. So first, maybe I'll show a video. Hopefully the audio will play. And this is an example. So this is a robot that we have at DeepMind. It's an Aloha bimanual robot where you have these two 7DoF, low-cost robot arms. And I set up this kind of office desk style scene. I promise it's not a curated scene. It's just kind of things I threw on the desk. And what we'll see now is me talking to this robot and telling it to do things.
Hi, how can I help you today?
We're going to clean up this table together. Okay,
What do
maybe
you
the
see
audio
in
is
front
not
of you?
doing its thing.
I see a yellow marker, a notebook,
Let's see.
a red
We'll try.
marker, a
Do you
green
need more
cloth,
things with the
a
audio?
pair of glasses, a glasses case.
They don't have audio out here. Yeah.
Let me figure out one sec.
Maybe
Yeah. I think this one will work actually. Okay, let's try this now. It's definitely going through. Maybe it's not turned on from somewhere. Okay, anyway, that's a bummer. Okay, so let's say there is a video here, and what we'll see in this video, maybe I can just speak over this video. I think it's playing. Okay, it's playing now. Okay, so what's happening in this video, it will move, I promise. What's happening in this video is there is this natural language interface where I'm talking to this robot and I say, what can you do for me and help me clean up this table? And hopefully any second now, it's going to start moving and it's going to start cleaning up the table. And at different points in time, I give it instructions. So if this works in the next 10 seconds, we'll do it. Otherwise, we'll just skip. So I'm telling the robot, okay, I want this table to be clean in a certain way. So can you pick up these pens and put them in the pen holder? Can you pick up, the calculator and put it in the basket, or open the notebook, draw a line in the notebook? And this is a lot more impressive when it actually does that. So it's okay. It does that. I promise. It's on YouTube. It does that. So what I wanted to go from here is essentially say, this is an interaction we kind of cooked up in a very limited setting to understand this question of what it might mean to have a robot that that can be general, that can do anything. And to make this less ambiguous, if you had seen this video, this slide would be very obvious. But what I'm going to do is give a somewhat concrete definition of what version of generalist policy was shown in the video in the previous slide. So we saw a combination of the single arm and bi-arm skills where you have sometimes a robot just does things with one hand, sometimes it uses both hands, and it's manipulating with its environment, it's picking things up. It can do a lot of different skills. So this is just one policy. We're not switching between different policies. You have this one large neural network where you ask it to do things and it can pick things up, pour things, open drawers, close drawers, play with a lot of different objects. You could just take something out, put it on the table, and it would do things. And it works in different lighting conditions with background distractors, lots of initial positions, and so on. So one version of one characteristic that you would want a robot like this to have is that it can do a lot of things, not everything, because that is not really a falsifiable definition. So it can do a lot of things. And if you define a set of things it can do, you can try to ask the robot to do it. And it can do all of this while being very steerable by understanding what the human is saying in natural language. It doesn't have to be speech. It was on the previous slide, as you clearly heard. It was me talking to the robot, and it was the policy understands what I mean when I say, no, pick up the red marker with the right hand and put it in the left side. Like, it understands language. So very, very, very broad strokes. What I want to highlight here is there's maybe two somewhat orthogonal capabilities where there is a notion of generalization where the robot can work in a lot of different settings, not a limited set of things. And while being general, it is also steerable. The way a user wants to interact with the robot, you can guide the robot to do certain things in certain different environments. So in today's talk, what I'm going to do is spend a little bit of time talking about both of these sections. What does it mean to generalize one version of it? And what does it mean to be steerable? Now, none of this is kind of a concrete definition you would put in a textbook. We're still kind of learning what the boundaries of what the frontiers of this of such models look like. So maybe I'll give a sampling of the current state of the art and how these models perform. So as I was saying, we'll do this in three parts, where we'll first talk about what generalization means, how you even evaluate it, how you put a number on it, and then eventually come down to how do we improve it, similarly for steerability, and eventually kind of putting all of this together into the video that we did not see a few minutes ago. So getting started, again, generalization is something that has so many different meanings to so many different people. It's really, really hard to get a very concrete version of generalization and to evaluate it in the real world. So in this project which we did with collaboration with Stanford, we're trying to understand how do you even go about measuring generalization? How do you report it? What is the language and what are the numbers that you use to go on? So the key question for this is what kinds of generalization do we care about? It's not just saying something is in and out of distribution. What are the different kinds of factors in that distribution? What do they look like? What are the different types in this out of distribution that you care about? And then eventually, how do you measure it? So just so that we're all on the same page, because throughout this day, you're going to hear the word policies and planners a lot of times. So for this talk, what is a policy? A policy is something that runs on the robot. We can treat it as a black box. It takes observations into the model. So it's a vision conditioned policy. We're in a vision conference, so we have to work with vision observations that are captured from your robot. It has some notion of an instruction. We'll say this is natural language instructions. It's a task specification, and it takes actions in the real world. So for the purpose of this talk, we'll say it's a vision and language input, action output policy. We now popularly call this VLA models, but it's generally a vision, language, and an action model. And the key insight we set off this work with was just to break down generalization in a very, very simple way with respect to the three different policy modalities. So the V, the L, and the A. So we have whatever you think is your task, what are the different ways in which you can perturb the different modalities and still continue succeeding. So as an example, this is a very popular data set called the bridge data set, where you have data that looks like this. You have a human teleoperator that goes to this toy kitchen. This toy kitchen has a sink, it has a knife, a carrot, a bowl. And there's a task called put carrot in plate where they do something like this. A good general policy should be able to, well, solve this task. Obviously, this is in the training data, but it should also be able to solve versions of this task. So one way to perturb the visual dimension of this problem is, let's say the sink was red instead of blue. Your policy should still work. The policy should not care that a background artifact in the environment changed. Similarly, instead of maybe calling it a carrot, you could call it an orange root vegetable, an orange object, and it should still know. This is like saying it should understand what proximity in the language space means. And similarly, on the behavioral side, if the carrot was placed somewhere else, it should still be comfortable understanding that this carrot needs to be picked up from this other place, and it should work. So our proposal essentially was to break down generalization in a very empirical way and define generalization as the robustness to perturbation along the different axes and modalities you care about. So for the context of VLA models, which we've been studying, this means the way to report generalization would be see how much you can perturb them along these three different modalities: the vision, the semantic, and the behavioral modalities. And the way you would do something like this is you would define so you start with a base task, which was the put carrot in the plate. You define some sort of a perturbation or a modification on top of this base task. You kind of group all of these perturbations into a broad factor, combine that into an axis, and then eventually to some categories, which is much easier to show in a visual way. So you start with a base task that looks like put carrot on the plate, and you define these kind of three broad types of perturbations you can make for your task. And oftentimes it's not just one of these three. There's like an intersection of all of these, and then you can go and make a list of all the different kinds of perturbation that fall under this. So it's not just that the background color can change, but the object itself can have different lighting conditions, different albedo. You can have obstacles that require new behaviors to be generated. You can have the human speaking in a different language or with some grammatical errors, and that still should be something that your policy can support. And so the exercise we did was we went through and looked through all the kind of tasks people care about and made this somewhat exhaustive list of 20 different ways in which people care about measuring generalization. And then we just concretely made this a benchmark where you take a task, you create versions of this task, and then you report how well your policy works under these different versions. So as an example of what this looks like, this is a tool that we made for people to use this online, where you would start with this doesn't need audio, so this will work. So you start with a task. In this case, it's still the carrot task, and you define some sort of base instruction, which in this case was the knife, and then you select an axis of perturbation that you care about. And for this specific case, we use off-the-shelf, generative image models to generate different versions of this task. So it suggests how you would generate these different things and evaluate them. And once we did this, you can now go and analyze what the current state of the art looks like. So we all roughly believe that we have really good vision language action models that are pre-trained on a wide set of data. So we started with this data set called the bridge data set, which is at least for its for what it was a few years ago, it was a fairly large behavior cloning data set with a lot of teleoperated demonstrations. We took a bunch of pre-trained VLA models, which represent the current state of the art. We collected in domain some demos for the kind of tasks you want to evaluate them in, and then we co-fine-tune the data. So rather than saying out of the box, every model should work on bridge data, we kind of adapted every model so that it works on bridge data the way you typically do. And then we through this taxonomy that we developed for generalization, we evaluated how these models work under these different perturbations. So now we can at least have a way of concretely saying, this is why the model has semantic generalization, or this is the extent to which it is robust to lighting conditions, which is eventually what you care about when you want to download these models off the internet and make them work for your task. And for our analysis, we started with a bunch of open source models, OpenVLA, which came out about a year ago, which is the first kind of completely open VLA model that's based on a language model backbone, which is actually tuned for bridge data. So it's a perfect baseline for something like this. On one extreme, we went to a more recent kind of lower capacity version of OpenVLA that runs faster, but it trades off kind of scale. So this allows us to understand the question, how much does the backbone actually matter, and how close are we to understanding the scaling dynamics for these kind of models? And we went to maybe the current state of the art, which was Pi0, a model that came out about 6 months ago, which has a different architecture, a different algorithm for predicting actions, and is generally seen as the new generation of VLA models. So we take all of these base models and we make this kind of spider chart with it. So to try to interpret it, don't try to pixel peep, but essentially we have these three big axes: the visual, semantic, and behavioral axes, and then the overlap of these axes. And we design each axis on the spider chart is a different perturbation that you measure on. So the black axis, which is the in distribution ID, is essentially what is being reported right now for all of these papers. And we normally look at the ID method and we say, okay, A is better than B, hence my model is better. And you can see that the three models that you see here, roughly, they do have some trending on the ID side. So they came one after the other. So OpenVLA was followed by MiniVLA, followed by Pi0. And as you would expect, the latest model is higher on the in distribution axis because this is what we have been reporting as a community. But when we start breaking out the performance and we factorize it into these different axes and how they perform under perturbation, we actually start seeing more interesting, more fine-grained behavior. So some changes actually help visual generalization, others help semantic generalization, some don't help at all. So I have a summary of some of our findings in this study. Generally, as you would expect, newer architectures are better. Pi0 used Polygemma, which was up until last December, kind of the state-of-the-art open source VLM, way better than something like Llama 2 with a VIT on top of it. And it shows because it has slightly better visual and semantic generalization, which is a really good thing. It generally seems like visual generalization, which is something, at least in the robotics community, people are really excited about solving. And in the vision community, people are excited about solving using transferable vision representations and so on. It generally seems like all of these models are really good on the visual axis, owing to a really good pre-trained VIT that we start from. It seems like changing slight lighting conditions and background distractors and so on generally doesn't break these models, which is great because for the longest time, we believed the problem was pixels and how we process these pixels. We also kind of started this VLA era by saying that we get semantic generalization for free because you're using off-the-shelf language and vision models that understand semantic concepts and they're beautiful. But we find in all of our experiments that they're actually not that good. We don't actually have a good sense of language grounding and proximity in the semantic sense. And in the second section, we'll try to go into why that might be the case. And lastly, this notion of whatever is called behavioral generalization, actually performing actions that are outside of the training data distribution, is surprisingly bad. And what this means is essentially, well, it shouldn't be a surprise to anybody outside the field, but inside the field, we've been kind of blinded by this BC regime where we just believe that large-scale imitation learning is going to help us generalize to out-of-distribution actions. And it specifically shows up in the behavioral axis, not as much in the visual and semantic axis. Very quickly, some other things. So some controlled ablations where we have the same baseline model, the same backbone, but it's trained on two different data sets: Bridge, which is the single robot data set, and OXC, which is this cross-embodiment data set. And it generally kind of satisfies the cross-embodiment hypothesis that adding data from other robots, adding that diversity of data is hugely beneficial for both visual and semantic axes. It doesn't help on the behavioral axis, so it doesn't look like cross-embodiment is helping generate new actions, but it is helping pre-train better features from the visual and semantic generalization. So generally, more data is good, more diversity is good, but unclear how exactly we should scale this up if we want to improve on the behavioral axis as well. Going maybe one step beyond cross-embodiment data is scaling from non-robot data. So in this case, we take a variant of OpenVLA that is co-fine-tuned on VQA datasets. VQA is visual question answering datasets, which are non-robot datasets. And again, we find that it hugely boosts visual and semantic axes. We can just, I think we can put this here. It's not here. It is here. Okay, we're gonna wing this for our next video. Hopefully it'll work. Thank you so much. So it usually benefits visual and semantic axes, which again makes sense. These VQA data sets was how VLMs were pre-trained in the first place. And if we use them right, it can actually help. Unsurprisingly, it doesn't really help, on the behavioral axes. So this maybe trying to break it out into these different axes can allow us to understand the trade-off of how VLAs should be trained. How do you preserve the generalization performance that VLMs get you? And we're very, very far. So this is, again, another place where we should be spending a lot of time on. Similarly, some quick takeaways. On the left, we have two different language model backbones, but the same architecture overall. And again, we see that a bigger language model backbone has slightly better performance. So generally, there is some x-axis where adding scale helps, but the improvement is not nearly as much as you would want it to be. So you just throwing a 2x larger language model isn't going to magically make your robot policy better. On the right, we have an example of a different thing you could do, which is purely algorithmic in the way you tokenize your actions and the way you represent outputs. And you see that the improvements from something like that, which is a very clever algorithmic trick, is way bigger than from training a 4x or 6x larger language model backbone. And there's a lot of room for these interesting small algorithmic tricks that can actually improve our models. And to give a sense of why this would be why this kind of characterization can be very useful, let's say you have any of your favorite models in all of these cases. And what you want to do with this model is eventually you have a robot in your lab. Let's say I have a Franca robot in my lab, and I want to solve a set of 5 tasks with it. Now, when I want this to work in my lab, I want it to work in a variety of different conditions. So here's a sampling of a robot we set up at Princeton, which is trying to do some kitchen tasks, very similar to what's on Bridge, but completely different kitchen, different tabletops, different drawers, different arm, and so on. So how do I go from this off-the-shelf pre-trained robot, which can do something for someone else, and modify it so it works for myself? And we found out that, well, there's no hope in completely zero shot any of this working. But the way we can do this is we can add some new data into our pre-trained model and then shape it and adapt it so it starts working for us. So this was a paper that we just put out on arXiv a couple of weeks ago, where we're guiding data collection by trying to predict what the scaling dynamics of a model like this looks like and how they grow over time. So when we're positioned with this kind of a question where what is the kind of data you should collect and what is the least amount of data you can collect in your robot, in your lab, to make things work broadly for your target application, we found out that this, I won't get into too many details. We have this formalism of doing a factored scaling dynamics where you start with any of these factors along your generalization taxonomy that you care about. You plot out a scaling curve starting with 10, 20, 50 demos of fine-tuning on this data, and then you extrapolate it to guide what kind of data you can collect. And once you do that, you can get a model that can work in a lot of these different conditions exactly for the kind of target scenarios that you care about. Okay, so we'll wrap up this section with some quick takeaways. At least if this was not obvious to anyone not directly working on these models, maybe the one-line takeaway for the last 20 minutes is we are pretty far from what you would call a convergence of VLA architectures. There is no single recipe that you just blindly start scaling up and it works, and there's a lot of room for algorithmic research. Data still remains probably the most important component of this puzzle. Just changing the type and quality of your data can massively affect your model. There's a lot of room for architectural improvements, algorithmic improvements as well. And to try to track these, you should break down your policy performance and try to analyze it in a more fine-grained way. Great. So this was about kind of the first piece of the generalist policy puzzle, the generalization piece. I want to move on to the steerability piece and then draw some connections to everything we saw in the analysis so far, where it seems like data is kind of really, really important. And the key thing we'll see here is it really, really matters what kind of data you're training your models with, both in terms of the diversity of data, but also the way the data is labeled and so on. And for trying to be somewhat concrete about what steerability means, again, the way we're going to use the word steerability in this section is is by measuring the ability of this kind of policy, which is language condition, which is task condition, to follow multiple different instructions in a scene. So if you set up this multitask scene, like the hypothetical video I showed in the start, there's a lot of possible actions you can take in the scene. And you want to measure how well can a user ask you to do exactly what the user wants by providing natural language. And this has to do with the language action grounding of your VLA. And in some sense, I'm going to argue that steerability is somewhat orthogonal to how well you generalize. You can measure steerability completely in distribution, and that would still be a valid thing to work on. And as we saw a little bit in our axis of generalizations along the semantic axis, there was a lot of performance drop when you change the instructions. So what I want to show you now is like an example of why that was the case. So in this case, we have, again, the bridge data set in a tabletop setting now where you have a scene with a spoon and a plate. And did the video play? Okay. Let me try again. Yeah, so on the top left, you have the scene where you ask the robot to put a spoon on a plate. And the robot does this. This is OpenVLA out of the box. It's really good at understanding what a spoon is and what a plate is, and it can pick up a spoon and put it on a plate. But if you try changing the instructions a little bit, let's say there's two spoons now, a green spoon and an orange spoon. And if you say, put the orange spoon on the plate, I don't actually think the model knows what an orange spoon is. I would argue it actually knows nothing about what a spoon is or what an orange is. It just kind of picks up one of the two things because it roughly aligns with its prior distribution without understanding which one of those two objects is tied to the instruction that's being given. Similarly, on the bottom left, we have this other example of 6 different objects, and we say pick up the green spoon and put it on the plate, and it succeeds. It can pick up the green spoon and put it on the plate. But then if I try to come up with a few different instructions in the same scene where I say put the broccoli or the green block or something else on the plate, it doesn't really understand it. It kind of just picks one of these things on random. And this is, again, not to pick on any single model or any single data set. This happens, again, on a completely different data set, on a completely different model where you say, put a red marker in the cup. It mostly kind of seems like it gets it. There's 4 or 5 different markers here. Sorry, the resolution's kind of bad, where you have a green marker, blue marker, red marker, and you say put the red marker on the cup, sometimes works. But if I try to tease out every possible instruction that's possible in the scene, we quickly find out that the model just kind of picks up one object at random. So it really doesn't understand what the task was. It is a really good policy. It's really good at picking up something and putting it at something, but it doesn't really understand what to pick up. And this is why when we eventually want these robots around us and to command these robots, they're just not ready for that because they don't understand the conditioning signal. So why is language steerability so hard? One possible hypothesis that we set to test about 6 to 8 months ago is that this is, in some sense, this is purely a labeling problem. It's not the case that our data is too small. In fact, both of these models were trained on a lot of data, but somehow something about the way we're feeding this data into the model, the way we're labeling these models, labeling this data is not good. And if you start to open your data set and read what data samples look like, we find that most data sets don't actually contain enough signal to ground the language in the action itself. And you get this notion of a posterior collapse where you don't need to listen to the language to actually solve the task. So if you look at these 3 examples at the bottom, if the task is move the spoon and the only thing that's in the table is a spoon, the only thing you can do is move a spoon. The robot never needs to understand what a green spoon is or what a yellow spoon is. Similarly, if the only thing in a drawer in the scene is a drawer and you say open the drawer, it's going to learn a good prior of opening drawers, but it doesn't really understand what the words open the drawer mean. And we see this time and again in a lot of data sets where most of these data sets have a lot of interesting behaviors, but they don't have enough diversity to actually justify understanding the semantic nature of these behaviors. So the simple idea that we started for this project was, let's assume that the data sets we're using are behaviorally diverse. They're big, they have a lot of different skills, and they're very interesting to learn from, but they lack semantic diversity. And if this is true, then this allows us to focus on one specific kind of diversity that we can very easily fix. So here, if you think that the data is informative, but it just doesn't have good labels, then you can go through a relabeling process and annotate the data with more interesting labels that you care about. So better functional labels, more maybe geometric things, more positional things. And I can give you an example of what that looks like. So let's say you have a trajectory data set. This is where we're operating in the tabletop manipulation setting. You have a data set of a lot of interactions of this robot with the environment, and you have some primitive skills that are captured in a very diverse sense in this data. So you have a lot of picking up of different objects, hundreds of objects, and you have a lot of different placing locations for these objects. So it's a lot of interesting pick and place data. And let's say, this is not fully hypothetical. This is a data set that was open sourced by Google about two to 3 years ago, called the RT1 data set, where you have thousands of skills of this one robot collecting a lot of pick and place and opening drawers and pouring things in this tabletop environment. And it satisfies the assumption. It is an extremely diverse behavioral data set, but somehow all the labels just look like pick object and place object, which is stupid, because now if I say pick orange object or pick object from the right, it doesn't really understand it because it never had to understand it. So what we'll do is we'll go through this relabeling process where we'll take each of these primitive skills, and using some extra signal, whether it's a VLM, whether it's a human annotator, we'll try to generate versions of these skills, like pick an object from a certain angle or in a certain specific way, or reorient it to a certain pose, or place it in the top left of the corner, or place it in the second shelf, something like this. And then you train the same policy. So we won't make any architectural changes, any algorithmic changes. We'll just change how the data is labeled, and test this hypothesis. Does this actually help? And to go into maybe some of the specifics, how do you actually annotate these things? It's not that hard. You can, the simplest thing we did because we were lazy was you just hand annotate a bunch of these things. And because this is teleop data by default, humans are not very good data collectors. So we had a lot of these different, diversity elements we could use. So one example was you take all of these different picking style behaviors, and you use forward kinematics to compose to calculate the grasp angle. And you take all of the grasp angles and you cluster them, and then you use that to annotate, was this picked up from the right side, from the left side, from the top, from the bottom. Really easy to do. And you can group this into clusters. You can have something else. Something else we did was we designed the table into like a 4x4 grid, and then we calculated which part of the table was something placed. So now you can say, oh, don't just place the object, but place it in the top left side of the table, or place it in the 2,3 position. All of this data was already present. We just annotated it in a very simple way. And kind of to cut things short, it kind of works. This was about a year ago, so VLM auto relabeling was not very good. I'll talk a little bit about how we improved that since, but even this very simple thing of just heuristic relabeling of a very manageable scale of data set, we already see that this green bar, which is our method called Steer, which is trained on the same model as RT1. It's the same architecture, same capacity, but just different data. We see a massive boost in the language following capabilities of these models, even compared to OpenVLA, which is a 10 times larger model trained on a lot more data, but not the kind of semantic diversity we care about. So we see that just blindly making the model bigger is a lot less valuable than perhaps trying to be more careful about how you curate your data. And as an example of what these behaviors look like, with Steer on the right, you can see that you can very clearly say pick up from the top versus pick up from the side is a behavioral mode that the policy now understands. And the reason we care about steerability is now that you have a way to command these models with very fine-grained instructions, you can use your favorite language model planning high-level policy to actually do this automatically. So let's say you want to solve maybe a somewhat complicated out-of-distribution task, which is multi-step. In this case, it's pick up this orange flower pot without disturbing the plant. Now, if you just put this instruction into your policy, it doesn't know what the hell you're talking about. It makes sense. But it's very easy now for any of your favorite ChatGPT, Gemini, VLM to take this as an input and break it down into a language that your policy understands. So in this case, there is what you would call some semantic understanding, which says if you don't want to disturb the plant, you should pick the pot up from the right. that is really simple. You don't need to train a robot to do that. It's very obvious, and it's captured in pre-trained models. So you start with any of your favorite VLM. The VLM is going to break this task down and say, okay, pick it up from the right and then move it up. And then once it's broken this down into simple parameterized instructions, you can give it to your policy, and then it'll run on the robot, and and things work. Similarly, you can do this for a much longer horizon of things, where again you use your favorite language model as a planner, nothing too fancy there. But because your low-level policy can now understand a lot of different kinds of instructions beyond just pick object and place object, you can go through this, through this process where you can have a VLM as an orchestrator for these policies and talk to it in somewhat natural language, in somewhat structured language. Let's not call it natural language. And here's a rollout of what all of that looks like. But yeah, so with Steer, you kind of always pick up the pot from the side. You never disturb the plant, whereas any of the other policies will just arbitrarily pick it up whatever way makes sense. And very briefly, what we found as an interesting output of this is, even though you might only relabel a set of objects that are in the data set, because these are still fairly high capacity VLA models, there is a lot of the generalization from pre-training that stays with you. So even though we only collected these primitives on the data that was present in the training data set, when we add new objects like this honey jar or this cup with beans in it, it still understands what it means to pick up from the side and pick up from the top, or put it in the top right corner. And that semantic understanding, which was maybe captured only for a small part of the data set, generalizes to completely new objects, which is great. So all of this is great. We finally figured out a way to make language models slightly more steerable. I wouldn't say it's fully natural language yet. But everything I described so far was manual labeling. This was the first author, Laura, designing all of these heuristics in a JSON file, or she was manually clicking on each data set and trying to relabel it, which is laborious. When we did this, VLMs weren't really good. She tried. But now that maybe VLMs are getting better and better, can we try to find different ways to automate this, which remains more scalable? And the other kind of maybe concern about the framing so far is we did assume that we have behavioral diversity, and the only thing we lack is semantic diversity. But what about cases where the behavioral diversity also is lacking? Can we think about ways in which we can do the similar relabeling process to make things work? So in the second project, which is a slightly different setting now, this is the same policy. It's a vision and language input and action output, but this is now a navigation policy, which is, instead of controlling a robot to do pick and place with a robotic arm, it's actually controlling a robot to drive in an environment and follow natural language instructions. And we found a way to kind of drop this assumption of behavioral diversity. So if you have a data set for navigation where you don't have enough behavioral diversity, we found a very interesting way to generate counterfactual actions, to generate completely new kinds of data using a suitable forward model, which I'll talk about in a bit, to widen the data distribution itself. So this now allows us to generate completely new data using data that's already present, like a synthetic data generation thing. And then we'll continue the thing before, which is we'll try to make the existing data a lot more informative by generating new labels. Maybe just in the interest of time, I'll skim through this a little bit fast with very high level things. So let's say, very similar to before, you have a base data set here. And for the most part, if any of you have worked in navigation, you'll realize that most data is actually kind of boring. Most data is driving straight, not interacting with any objects, avoiding collisions, being a nice robot. And hence, most of the labels that exist in your data are actually not that informative. They look like go straight or avoid collisions. So what we did there is, let's say you have access to a data set that looks like this, which is kind of a basic data set. And we have some high-level instructions for this data set. We pass this to a VLM to propose new tasks. So even though the robot went straight, if the data was collected in this room and it just went straight between the chairs, it actually saw a lot of interesting things on the side. And we use a VLM to propose a lot of these interesting things that it could have seen and it could have done. And then we use one of really nice kind of state-of-the-art navigation policies to generate, it's a generative action policy, to generate possible future actions that the robot could take to go to those things. So if the base data set was just going straight, you kind of sample, oh, what if I wanted to go to the person wearing a red shirt, and you generate fake actions. You can generate these synthetic actions of going to a person wearing a red shirt, and you annotate your data set with that action. So instead of just training on this blue trajectory, which is the base data set, you can actually sample all of these interesting green trajectories, which have not really been taken. So they're not as informative as the base data set, but they give you a lot of signal about possible futures that exist for the robot. And once you have access to this kind of a relabeling mechanism, which is now automatic because it doesn't need Laura in the loop to label these data sets, you actually generate a very, very large data set, which is maybe 10 times larger than the original data set. And this is a process we call CAST, or for counterfactual labeling for synthetic trajectories. So we start with this uncurated data set. We generate a lot of kind of possible futures. We label them, and then we train a giant VLA model on this. And now that we can generate 10 to 20 times the data that's in your pre-trained model, you can train a much bigger model. And once you can train a bigger model, hopefully it'll start learning some interesting things. So the architecture itself, I won't go into too many details. It looks about the same as a VLA you expect. It takes vision and language, goes through a transformer, predicts action outputs. But then what it can do is it can actually, compared to other ways in which people have studied language conditioning and augmentations in the past, it works really well. I can go into some of the details, but maybe you can just trust me that it works, and the numbers are bigger. But let's look at some videos, because videos are more fun. No audio here, so we can still listen to it. This is a sampling of maybe the different behaviors that you can train that are not in the training data itself. So in this case, on the top two, by the way, they're not playing. In the top two, why is it not playing? Nope. We just skipped. Okay, it doesn't want to play videos today. That's so weird. But we found that we can actually start conditioning the model with new objects that it's never seen before, but also new kinds of behaviors that it's not seen before. So for instance, at no point in your training data were there instructions that said, move along the bench. That's just not an instruction people generate. But it could be an interesting instruction to have if you have this robot going through a crowd. You want to say, move close to the bench, pass the person on the right, take the door that's the second from the left. And all of these instructions, while it's really hard to always go and tell your operator robot to collect these instructions, it's relatively easy to generate synthetically a lot of these instructions. And again, you have to just take my word for it that it actually does that. Okay, quick takeaways. A lot of data sets, not behaviorally diverse. When that is the case, sorry, they are behaviorally diverse, not semantically diverse. When that is the case, relabeling is a great thing to do, and you should do as much as you can. When this assumption is not true, you need a way to generate more behaviors that are not existing in your pre-training data, and that's where this notion of counterfactual sampling comes in. We showed some results for the counterfactual sampling on the navigation side. We're still working on expanding this to more higher degrees of freedom for manipulation, for bimanual manipulation, and so on. Okay, I have a few more minutes. So what I want to do next is maybe jump a little bit into what all of these kind of simple ideas combined might look like at scale. So we'll try to do the videos again from the start. Hopefully they will work this time, because it's annoying when they don't work. But what I want to talk about in this section is take a lot of these simple ideas that have come out from at the level of research papers with students, and put them all together into a very large scale VLA, and let's see what this means. So for the last year, I've been at DeepMind, and we've been trying to train VLA models and on large scale foundation models like Gemini. And we just announced Gemini Robotics a few months ago, which is a large pre-trained model for bimanual dexterous manipulation that can do a lot of things. And I'll give a quick overview, just as a disclaimer. I might not be able to answer a lot of technical details and questions for this section, so we can get into details of the other sections. Here, well, I mostly want to focus on maybe drawing connections to what has been possible by doing all of this in a more kind of principled, high quality engineering way, and then draw ties to how we evaluate this model, how well it generalizes, how we knew that it generalizes and doesn't generalize, and how it is steerable in language and so on. So as an overview for for people who aren't aware, we announced this thing called the Gemini Robotics project, which we start from, early this year, Gemini 2.0, which is a state-of-the-art vision language model, Gemini 2.0 Flash. We start with this giant VLM, which is way larger than anything you can fit in a single GPU. The first step there was to make the model better for the kinds of robotics tasks you care about. And that goes beyond just predicting actions directly. It goes into understanding semantic key points, predicting bounding boxes, predicting grasp angles for things that are present in your data set. And all of these things, because you can generate data pairs for them, like input, output, VQA style pairs, you can actually SFT any VLM to be good at this stuff. So what we did was we started with maybe the best VLM that was available to us, and we tried to make it better for physical and embodied reasoning, so that when we're ready to fine-tune it with actions eventually in the VLA sense, it already carries a lot of these pre-trained capabilities in them. So we went from there. We collected a lot. We have a large fleet of teleoperated data collection, primarily for the Aloha robot, which is what you see in the top. And over the course of 12 months, we have thousands of hours of data of a lot of interesting behavioral and semantic diversity of solving all sorts of different tasks. And once we have a lot of this data, using some interesting algorithms, we train this Gemini Robotics VLA model, which is this pre-trained model. And I'll try to show a video again of what that looks like. And once we have this giant pre-trained model, it's interesting to study how this can serve as a foundation model for a lot of downstream tasks you care about. So in this case, how do you make the model more dexterous for a single robot that you might care about? So we went and tried to teach the robot how to do origami, which is really, really hard to do with a low-cost arm that has no force feedback. We try to adapt it to complete new embodiments like a humanoid robot or bimanual Francas, trying to do industrial-grade tasks. And how do you specialize it just for reasoning at the cost of maybe something else where it can do completely new multi-step reasoning. Like if I want to pack a lunchbox and I'm vegetarian, which of these things should actually go into my lunchbox? And how do you kind of use the VLM and the VLA together to do these things? And the exact model that that ties to everything else today is a Gemini Robotics model, which looks maybe something like this. So you have very similar to maybe how you define a VLA. You have this robot policy, which has a multimodal prompt. The prompt has a language instruction, a natural language instruction, as well as visual observations, which is the observations taken by a camera that's on the robot. And then condition on these actions and instruction, you have this Gemini Robotics VLA, which is, like I said, it's probably so large that you cannot fit this all on the edge. So we had some interesting tricks to split this model between something that runs in cloud somewhere in Nevada and something that runs locally on your robot really, really fast. So the thing that runs in the cloud is actually the thing that's doing a lot of the high-level reasoning and a lot of interesting semantic reasoning. But then eventually, because you want this policy to run 50 hertz on the edge, be super reactive, you have a part of the model that runs locally, and there was a lot of interesting infrastructure work that went into making this work. So you have this hybrid model, which is part on device, part in the cloud, taking actions in the real world, take updated images, updated observations, put them back into the model, and go ahead. So when I say Gemini Robotics VLA, this is kind of what it means. It's a model that runs part in the cloud, part on device. It's a giant VLA trained on a lot of data with a lot of pre-training, and it can do a lot of diverse tasks. So just to show maybe a sample of a single model, a single policy trained on this robot can solve hundreds and thousands of different tasks, which honestly at this point is really hard to even enumerate. But what we reached with this is we reached a point where we actually feel confident that for a set of, for the definition of generalization that I opened this talk with, for a set of skills, you can literally ask the robot to do anything with certain objects, and it'll behave predictably. It's not fully there yet, but that is the goal. And to measure how close we are to that goal, let's go back to StarGen, the generalization taxonomy that I opened the talk with, where we're trying to look at how well does this model perform under these different axes of perturbations that we care about: the visual, the semantic, and the behavioral. So to talk about visual, as a reminder, visual means if you have a policy and a base task, if you change things about the visual observations without changing the task itself, how quickly does the policy degrade, or how well does it work? So in this case, if you have an in-distribution task, which is put the grapes in some compartment of a box, which is a fairly interesting task. In distribution at the top, models can do fairly well. But what happens when you add distractors? What happens when you change the background, the table texture? What happens when the lighting condition changes? When you have here, like you have the saturating, very highly saturating bulb here, which can completely change observations. And you see that across the board, well, in distribution, the model's great. That's fine. Nothing to flex there. But the interesting things are out of distribution, once the performance starts degrading, we notice that very similar to what we saw for open source models before, visual generalization is generally something that is maybe not the most important thing, where we see drop in performance, but for the most part, the model is completely fine with different lighting conditions and different backgrounds and different distractors. And partly owing to maybe a big VLM or a big pre-trained VIT with a lot of good data, but looks like on the visual side, we're covered. The other axis that we talked about was semantic generalization. So if you have a task, let's not change anything about the task except the instruction that needs to be executed for the task to succeed. So same task, put the green grapes in some part of the box, and then we create a few different perturbations of that task. So we have a typo where there's a lot of spelling mistakes. You have a different language, which at this point, I don't remember, maybe it was Spanish, I don't know, with a different language, we rephrase it with like different parts of speech. So it's the same task, but it's like this complex thing, which language models can solve very easily, but an existing small policy might not be able to. And then we change kind of the description of different things. And again, this is where we see things like typos, new languages, description. If you have small VLAs like the Pi0 model that we're studying in yellow, or something like a diffusion policy, which is in green, they just kind of don't know what these things mean because they were never pre-trained with these kind of variations, and they completely start breaking. Whereas, well, even shockingly, even the Gemini model actually struggles with a lot of these things, but it performs fairly better. So continuing some of the takeaways I had in the first section of the talk, it kind of seems like semantic generalization should just be solved by starting with a very, very good language model. But we still see a lot of performance drop, and it's worth understanding why this might be the case, why pre-training with state-of-the-art language models doesn't give us, typo resistance for free, which is weird. And lastly, kind of coming back to the third axis, which is behavioral generalization, where you have maybe different initial positions or different instances of the object and try to measure how performance drop. Again, we've made some progress in getting slightly better behavioral generalization, but there's a long way to go. I'm almost at time, so I want to quickly mention steerability eval in a way similar, where you have a task and you have a lot of different tasks that can be done in the same scene. So you can start with different objects, put them in different places, different versions of a task, and we try to evaluate what this looks like. And here's where we see massive gains over existing open source state-of-the-art models, where some of the ideas I did present in section 2, some of them I didn't, which we were focused on making the natural language interactivity and steerability really good. So you have a model that you can actually talk to, and you can ask it to do anything and put it anywhere, and it kind of sort of continues working. And I had some videos of it working, but I think because of my time, I'm just going to start skipping to all of these things. And give me 1 second. My laptop is stuck. It will become unstuck soon. Okay, so that was everything I had for my talk. We talked a little bit about generalization, a little bit about steerability, and how some of these things come together if you want to do this at scale with very, very large models. I do want to very quickly mention we mostly focused on the data side of improvements for making models more general and more steerable, but there's a lot of different knobs that we have access to. We have some interesting work appearing at RSS in 2 weeks from now, talking about how better visual and spatially grounded representations can help generalization, and they can improve a lot of different reasoning capabilities along the visual axes, maybe not the other ones. We've been exploring how we can use video generative models as a completely new data source in addition to what is your typical real world data collection, and how that can augment and provide a lot of different capabilities. We've been thinking about what data goes into these models, how do you curate your pre-training data distribution, how the data is being mixed, and so on. And lastly, no matter how good these models get, they'll probably never be enough to just work by themselves. And we have a lot of interesting explorations on what comes on top of these models. How do you plan with these models? How do you orchestrate these things, include memory, and so on? I want to do a quick shout out to all the people who led these projects, my collaborators at Stanford, Berkeley, Princeton, and Google DeepMind. And whatever time we have for questions, we can do it now, or you can find me after the talk.
Are there any questions from the audience? Oh.
Go
Yeah,
ahead.
sure.
Maybe the mic, yeah.
Yeah. People always will
Thanks for the presentation of the second part that we're talking about.
About what? Sorry.
So,
Oh, CAS. Yes, yes, yes.
so I see you are generating a possible future. So is it something synthetic? So all the videos are actually real and possible futures you generating. Is that synthetic?
So we don't generate pixels, we don't generate frames, we generate just actions. The actions are synthetic. So it is so we have this, there was a separate model which I didn't go into the details of, which generates actions conditioned on the image. So what you would do is you would take a real image which was captured and generate possible future actions which you can use as labels, but not actually generate pixels. And the model itself doesn't need future images, so you just kind of calculate you use the synthetic actions at existing frames.
You need some rewards, right, for those.
Oh, this is purely BC. There is no rewards. Yeah, so the model is trained with a prior of collision free. So it is kind of filtering clean actions that we're sampling from the model. And then we take those clean actions and we put them in the data set.
Other questions?
Okay.
This two model framework that you used, where you had like one big model
Mhm.
and one small model. What was the frequency at which both of them was the big model just running once, or?
So the big so there was asynchronous execution. So the output of the model that runs on the edge is 50 hertz. The model that runs in the cloud that runs at maybe 4 hertz, something like that. And it is asynchronous. So even if that model is kind of delayed because it suffers with all the internet latency and things that come with it, usually the way it works is you run the model in the cloud every, let's say, 300 milliseconds, 250 milliseconds. It gives some latent representation of the local model, and the local model is running much, much faster, and it's predicting actions at a faster rate.
Do you see that soon, like you would be able to just do it on the locally, or you think you'll need this stuff?
I think it depends. I think you can do it locally. So we have some effort in trying to make this entirely local. And for that, you would operate at a different scale. For instance, if you want to run this on a 4090 on-prem, the largest model you can probably run, it looks like an 8B model, something like a Llama 2, Llama 3, 8B grade model. But if we believe that bigger models are better for something, then there will be a use case for a big model with a small part that's local. I think there's a lot of reasons for on-device to be preferred because of security, latency, connection issues, especially in robotics. But I think at least at the grade of identifying what the frontier of these models looks like, I think the scale of models we're playing with, we do not have the ability to load them fully locally, unless you want like a B200 cluster under your robot, which we're not allowed to do. But yeah, just. Okay.
Maybe I had a question for the case where you showed in the last part of the talk regarding the Gemini 2.0. In the different position, when you checked for different position, I saw the model actually had slightly better performance than the in-domain data. Like, you have some insight on that, maybe?
That's a great thing. I was hoping nobody picked on this. It is. I think this comes down to it's really hard to evaluate models in the real world. And one of the things we realized is so what does it mean to have different initial positions? It is essentially you have a set of training positions and a set of held out positions. The problem is when you're doing things at this is true for language and vision models today too. It's really hard to define what the boundary of the in and out of distribution is. So in this case, we tried really hard to in hindsight, go look at our training data, find clusters of where data has been collected and not been collected, and then sample OOD positions. But when the amount of data you're talking is tens of thousands of hours, it's actually really hard to make a true out of distribution. So even though here, when we said like different initial positions, we tried our best, but it's very likely that there was probably no fully out of distribution initial position. And the model just kind of resonates. So maybe the way I would interpret that curve is different initial position, it kind of just works as well as in distribution. Maybe the better way to look at these curves is not across the different modalities, but maybe across the different models, because all these three different models were trained on the same data. So if you want to compare architectural things, maybe the way to look at it is there. But I fully concede. I think this was very challenging, and we considered different ways to mitigate it, but we had already collected the data, and there was almost no way to report it.
So it's basically the pose of the initial a view of the robot towards the scene, I guess, right?
Yeah.
Okay,
All right.
thank you.
Thank you.
You're done?